In this video, I will talk about simple regression model in R. Before you watch this video, please make sure that you have watched my other video called Simple Regression Model. So I have opened up here the R script and I have already downloaded the data. These are the two data files that we would need. And I have put them into this directory here. And I have highlighted so far of the program and I have hit run here. And this is the console, which is typically at the bottom here, but I have moved it to the side for you to see a little bit better. And this is the results that we have here. So today we will talk about a simple regression model and interpretation of the results and coefficients. Then we will talk about prediction after regression, about goodness of fit measure, including R squared. And we will talk about the log forms, which is the log-log, log-linear, linear-log, and just a simple linear model. So again, these are the data files that we would be using. And we would first clear up the workspace that we have here. And then this is the directory where I store the data. So you would need to change this depending on where you store the data. And we would assign this location here as directory. We would also be installing packages. So we would be installing Tidyverse, Stargazer, and Migrator. And here in this loop, it's just ensuring that the packages are downloaded, updated, and loaded. Okay, so simple regression. We would be using a CEO salary example for this regression. So we would be using the file CEO salary one, CEO cell one.csv file. And for me, this file again is located in the directory. And this directory is the path to the directory is right here. So you can actually copy and paste this directory straight into here as well. So now that the data is read, we would be calling this data frame CEO cell 1, the same name as here. It doesn't have to be, but that's what we're going to call it. And so now let's use this data frame that we have from here above. And then we would be selecting only two variables from here, salary and ROE. And so we would only be retaining now two variables, salary and ROE. So if we actually look at the structure of the CEO cell 1 data frame that we have here, now we have only the two variables that we selected up above here. So they are salary and ROE. And here for salary, we have these are the first few observations. And for ROE, return on equity, this is the first few numbers that we have here. Stargazer summarizes the data frame as text. So this is the table of summary statistics. We have 209 observations, and these are the mean for salary. And this is the return on equity. So again, mean salary in terms of thousands of dollars. And so basically $1.2 million. And then ROEs in percentages. So we have 17% return on equity. The first 10 observations we're going to get by using head, the data frame, comma 10. And so here we have these are the salaries in thousands of dollars of the CEO. And this is the return on equity for the firm. Next, we can explore the data and we can find the correlation of the variables in this data frame. So here we have the correlation between salary and ROE is 0.11, so we have a fairly low correlation. The next thing, let's actually pick up and calculate the average salary. So here is, we are going to be calculating the mean of salary. So this is how we're going to calculate the mean of the variable salary. We're going to give it the name of average salary and mutate basically um, by calculating this, we will also keep this in the data frame as well. So later we would need this value. Okay, so how do we run a simple regression? So a simple regression has the formula of salary. This is our dependent variable, the one that we're trying to explain, equals beta 0, which is the intercept, plus beta 1, which is a coefficient, also called the slope here in a simple regression, and times ROE. ROE is our independent variable, plus U is the error term. So this is a simple regression because we only have one independent variable, which is ROE. Okay, so this is the model that we would be estimating, a simple linear regression. The way we do that in R is we're going to be running a linear model. LM stands for linear model. Here's the formula, which would be equal to salary is our dependent variable tilde, and here we list all of the independent variables. In our case, it's only ROE, and then comma data is our CEO cell. So basically this is the same data set that we're calling from right here. And once we estimate this linear model, we would be assigning the results here as model underscore CEO cell 1. So we're giving it this name here for the results. And if we use summary and then we basically call this model here, that would give the summary results from the regression. Okay, so if we run these few lines, this is what we're going to see here. So the model actually executes everything quietly currently, but if we summarize the results from this model, this is what we're going to see here. So this is basically repeating the formula. So this is a simple model of salary regressed on return on equity using this data set, CEO cell 1. So here we have the coefficients listed for the model. So the first coefficient is the intercept. So this is the coefficient on the constant in the model, and this is the value for it. And then this is return on equity, that's the variable. This is the coefficient, so the estimate is the same as the coefficients here. These are called standard errors, t-value, and the p-value. We are going to talk about these later on. Okay, so now how to interpret these coefficients. So the way to interpret the coefficient is that if return on equity increases by, and because this variable is already measured in percent, we're going to say by 1%, but because that's the unit, here we would have that CEO salary would increase by 18, and because it's measured in $1,000, that would be $18,000. The way to interpret the intercept here is that if the return on equity is equal to 0, and maybe no firm in the data had such return on equity, but if the return on equity is 0, then the salary of the CEO would be $963,000. Okay, so this is how to interpret the coefficients in the simple regression model. The next thing that we would learn how to do is to plot the observations with a fitted line. And so for this, we are going to be plotting, and the plot would take two arguments, the what's going to be on the x-axis and the y-axis. So on the x-axis, we would have ROE variable from the CEO cell 1 data frame. So basically from this data frame, we're going to pick the ROE variable, and the Y variable would be from the same data frame, we would have salary. And we would use AB line here. And so basically we would have A would be model CEO cell 1 $ coefficients, and we're going to be picking up the intercept. And B, we would be doing the same thing, and we would be picking up the coefficient on the ROE. So in other terms, what we are going to be using is the intercept here, which would be this number. And we would be having as B, that would be the slope for the ROE variable. So that would be the coefficient of 18.5. And so once we give the intercept and the slope, so the intercept would be A and the slope would be a B, here in color red, we would be actually plotting this. So when we execute this, here's what we're going to have. And on the horizontal line, we have the ROE, return on equity. So this is basically in percent. And here we have the salary on the vertical axis here. And so these points here are the observations. So each of the observations has a certain return on equity and a certain salary for the CEO. And now, once we have these points here, our linear model would be this. And so this AB line would be basically summarized of the linear model that we have. The intercept, if you look at the intercept, it would hit this line here at exactly this 953 here. And then the slope of this line would be 18. And this is basically that coefficient that we have here, the coefficient on the return on equity. And again, we have color red. So this is basically how this would look like. So we have the actual values, and here the predicted values, or the fitted line, are the points here on this line. So if this is the actual value, the predicted value would be a point right here on the line. If this is the actual value here, the predicted value would be right here on this line, the fitted value, and so forth. Okay, so let's continue on. An alternative way to plot is to use the ggplot package. And so here we could use ggplot for data. We're going to be pointing out to this data frame. Mapping, here we would have X would be ROE, Y would be salary. So we're giving it again the X and the Y. Here we would have setting the theme of this plot that we have here. And then we have geom points, that these are going to be points And geom smooth would be method. We're going to give it linear model. And standard errors false because we're not going to be having plotting standard errors here. So this is again an alternative way to the plot that we have up here. So let's go ahead and run this few lines here. And again, this is what we are seeing. Basically exactly the same thing as before, just using this package here, ggplot. So again, we have ROE, salary. So this is the independent variable. This is the dependent variable. The dots here, the points are the actual data. And the blue line here is the linear regression model. So these are basically the fitted values here. And again, we have the intercept is right here at about 953, and the slope of this line is 18. So basically, uh, if ROE increases by 1 unit, which is 1% in this case, then salary would increase by 18 units, and the units for salary are $1,000. So next we can do the same thing using um, another data set. So here we can use the wage data set. So we are going to use read.csv to read the wage one data set, which is a CSV file. And we're going to call this data frame wage one. And so from this wage one, we are going to be selecting just wage and education, just two variables. So we are selecting wage and education, only keeping those in wage one data frame. We're going to see the structure of this data set. We're going to summarize it using the Stargazer. This is the data frame, type equals text. We're going to use head of the data frame, comma 10 to see the first 10 observations. And then we will estimate a linear model here. So linear model, wage is the dependent variable, tilde education is the independent variable, comma wage one. Wage one is basically the data that we have here, the data set, the data frame. So once we estimate this linear model, we are going to assign the results into model underscore wage one. This is the name we're giving it. And then we can use summary of the name that we've given here to see the coefficients. Okay, so let's run this part here of the script. And this is the wage example that we see. The structure of the data set is now we only kept two variables here. These are wage and education. 526 observations. This is how the first few observations look like. Stargazer summarizes the data. Again, 526 observations. The mean wage is $5.89, and the mean number of years of education is 12.56. So the first 10 observations of the data set for wage and education. So the first individual has $3.10 as wage and has 11 years of education. The second individual has $3.24 as wage and 12 years of education, and so forth. And here is how we're estimating the model, linear model, and the formula is wage regressed on education, wage dependent variable, education independent variable using data wage one. And we are summarizing these results here that we pointed. So again, this is repeated the formula that we have here, and we're going to concentrate on the regression output. So these are the results here. And this estimate is the same as the word coefficient in our case. So here we have the intercept is given as this number, and this is the variable education, and this is the coefficient on education. So now the way to interpret this coefficient is that if education increases by 1 year, wage is going to increase by $0.54 because that's how wage is measured. And if education is equal to 0, although in our sample nobody has 0 years of education, we would have that wage would be minus $0.9. That's why this doesn't make sense, because no one has education of 0 in our sample, but it's basically showing where this line here is going to hit 0. Okay, so this is how to estimate and interpret a linear model with the different data sets. So now let's talk about prediction after regression. So for this, we're going to be using the CEO salary example again, and we would be using the data CEO cell 1 that we called up above in the same R script, and the model CEO cell 1 that we already estimated. So R stores the results in the data set, and we could just call it at any time later in the program. Okay, so now let's talk about predicted value for the dependent variable. So the dependent variable is salary, and the predicted value we are going to call salary hat. So salary with like a symbol like that, a hat on top of it. So here is spelled as salary hat. So salary hat is actually stored as fitted of the model CEO cell 1. So every time that we storing regression output and regression results in model underscore CEO cell, we can actually call different elements of this regression results using the specific element name here. So fitted calls the fitted values, and then we're giving it the name salary hat. And so we're mutating the data set by actually also appending this variable into the CEO cell 1 data frame. Okay, so now we can use Stargazer to summarize the CEO cell 1 data frame, and then we would be using ggplot to plot these results as well. So let me just go ahead and run this part here. So here we have, again, we have called the fitted values or the predicted values from the model. We name these as salary hat. We use mutate to basically assign it back to the data frame, and we're summarizing everything. So notice now that we have salary, our original variable, that's the salary. ROE was the independent variable, that's the mean of across all of the 209 observations. And we calculated average salary that earlier on in our script, and that's this value. And then salary hat, the average of this value is also the same number. So if you notice, the average of the salary is this number, and obviously average salary is that same number, but salary hat here is the uh, is also the same number. And so we actually that's always going to be the case, that the average of the predicted or the fitted value would be the average of the actual variable here. Okay, so now let's use ggplot again using data equals CEO cell 1, so same data set. Here we are going to be using, uh, so here we're going to be mapping uh, for X, we would have ROE, return on equity, but for Y, here we're going to be using geom points, so we're going to be using points, and we would be using for Y salary. We're going to give it one color for salary, and then salary hat, we're going to give this another color for fitted values because salary hat is our fitted values. So again, these are the predicted values coming from the regression model. And then we can actually also append a X label calling return on equity here as well. So this is what we are going to be seeing here. So this is the graph. So we have the return on equity is plotted here, and here we have salary. So notice that here for the color of salary, this is basically the actual data that we have here. And for the fitted value, notice that all of these points are on a line because that's what the fitted values are. They are basically predicting the points here on the line. And so again, we have uh, a different way to plot this regression line here by just plotting the fitted values. Okay, so now these are the fitted values. How are we going to obtain the residuals? The residuals now are what is an actual value minus the fitted value or the predicted value. So if you have this minus the predicted value, that's going to be the residual. Or this minus that, that's going to be the residual. So if we have this point is the actual value minus the predicted value, that's actually going to be a negative residual. So the way to plot residuals is basically because we have this here as the line, the regression line, if we attempt to plot the residuals, what that's going to do is going to collapse that line, collapse it, and it's going to be centered around 0. So remember how this data looks like, and what I will show you on the next, with the next graph is that this fitted values are going to be collapsed here around 0, and that's going to show you the residual, which is the actual minus the fitted value. Okay, so here we have the residuals. So here we are going to be calling the residuals from the model CEO cell 1 here. And these residuals here are going to be included in the data set using mutate. So we're going to append this to the data frame. So we're going to be using Stargazer here to summarize the data set. So let's go ahead and do that. And then we would be using ggplot to plot the residuals. Okay. So we are calling the residuals from the model CEO cell 1. And then we're going to call these U hat, and Stargazer will summarize these. So notice now that we have the residuals here, and the residuals actually sum up to 0, or the mean value of the residuals is 0. So actually this is not coincidental that the mean of the residuals is 0, because we have this as one of the properties of the ordinary least squares estimates is that the residuals would sum up to 0. Because U hat sums up to 0, this is why we have that the average of the salary and salary hat are the same, because these residuals is the average of them is 0. And we know that salary equals salary hat plus U hat. So the actual value is equal to the predicted value plus the residual. So this is actually always going to be the case. Now, using ggplot, we're going to call the same data set. We're going to plot ROE on the X line. And here we would be plotting salary. And then we're going to be plotting here the residuals using a different color. And this is the graph that we're going to get here. So notice that these are the actual values here for salary. I told you to remember how that looks like. And notice how the residuals here look exactly the same thing, but they're centered around 0. So notice that again, if we're using and we want to do a linear model, the linear model looks something like that. That line comes through here. And so what the residuals are the actual minus the predicted value. And so what basically the residuals are flattening that line. And now those points are centered around 0. They're no longer centered around that fitted values, but around 0. So this is basically what this accomplishes here. So now let's see the first 10 observations of the data. And so here are the observations. This is salary. This is the return on equity. So dependent and independent variable. The average of the salary is obviously the same number. Here is the predicted value salary hat or the fitted values. And U hat is the residual. So U hat is the difference between salary and salary hat. So if you notice this number here minus this number here is exactly this number here. This number here minus this number here is this number here. So if the actual value is below the predicted value, we have a negative residual. If the actual value is above the predicted value, then we have a positive residual. And then all of the residuals sum up to 0 of all of the data set. And the average value for salary here is the same as the average value for salary hat here. And that's that number. So these are again properties of the OLS estimates. Okay, so now we can graph the actual and predicted values and the residuals using again ggplot. Let's go ahead and do that. So here we have now all of them. So we have, this is our fitted line here. So that's the linear model. The actual values are right here. These are the actual values. And then we have the residuals are right here. You see the residuals are centered around 0. The actual values would be centered around the linear line here. And so we basically have everything plotted with one line. Okay. So we can do exactly the same thing for the wage example. And for this, we will be using the data wage 1 and the model underscore wage 1. So these are the results from the model that we estimated. And here we would be having, the first thing is we would be calculating wage hat, which are the fitted values coming from this model. And then U hat would be the residuals from this model. And then we would be plotting these observations here. Okay, so let's go ahead and do that. So here we have Here we have the true values are in purple, and the residuals are right here centered around 0. So the residuals are centered around 0. So this is the linear model line. So notice that the intercept was negative. You see like how it hits here below 0. And this is the slope of this line that we have here. So again, actual values in purple and the residuals are in green here, and they're all centered around 0. So next, let's talk about goodness of fit measures. So one goodness of fit measure would be the R squared. And what the R squared is showing is basically what percent of the variation we can explain with the regression, and the rest would be due to error. So here we have, again, the CEO salary example using the same data set, CEO cell 1, and these are the model results that were stored earlier. The structure function would be used to show what's included in the model or its summary. So here, this is what's included in the model, and this is the structure of what is included in the summary of the model. So here's the structure of the model. Here we have the coefficients here. And notice that the coefficients here are 2. That is the intercept that we saw before, and this is the second coefficient. So this is basically the coefficient on the ROE, and this is the intercept. So these are the values of the coefficients, and these are the names of the variables for which these coefficients are. It's also storing the residuals. Okay, so the residuals are these, and the residuals for the first, second, and so forth observations. And I think this is, and then we also have the fitted values here as well. What else is important in this long list here? We can also see here the data frame, how many observations and variable names. And so here we can see the first few observations for the variables. And then the structure that we have for the summary of this model. So basically, this is where the coefficients and everything are kept. So here we have several interesting things. So again, residuals are stored here. And we have the coefficients being stored here as well. Um, and we have R squared stored here. So R squared is actually one of the elements of the here in that summary of these regression results that we have here. So long story short, because this R squared is in the summary uh, here for the output, we can basically call it by using summary of the model. And so here, summary of the model, $sign, and then we have R squared. And so basically when we call this, we are basically going to have, this is the R square. So the way to interpret this R square is that 1% of the variation is explained with the model and the rest is due to error. So basically, we have very low goodness of fit here, very little ability for the model to explain the variation in the data. We can also use here the number of observation function to see the number of observations, and this is going to be 209. We can repeat exactly the same things using the wage example here. And so we will be using the structure for the model. So here again, the most important things are the coefficients. This is the intercept, and that is the slope for education. So here's the intercept, and that's the coefficient or the slope for education. We have the first few residuals listed here. We have the fitted values listed here as well. And then we have the R square is listed right here. So if we use summary model and then $ R squared, we would be getting basically exactly the same number as this number. So the way to interpret it is that this model for wage explains 16% of the variation in the data and the rest is due to error. And we're also storing the number of observations here as well. Okay, the final thing that we will do here is talking about log forms. So basically when the dependent variable is in logs or the independent variable is in logs. Notice that we still have a linear model, which means linear in parameters, but basically the variable is transformed. So we have log form transformation. Rather than the model itself is not log model, the variable is in log, so that's a transformation or a form. So we're still going to be estimating linear models. So here, let's read the data set here, and we would be calling it into a different data frame. So from this new data frame, CEO cell 2, we're going to select salary, log salary, sales, and log sales. We are going to basically just see the first 10 observations. So let's go ahead and run this part of the script. And this is how the data looks like. So again, we have salary of the CEO for a firm. These are in $1,000. We have log salary. That's the log of this variable here. So we have sales, which is measured in millions of dollars. And this is the log of sales that we have here. Okay, so this is how the data set looks like, and we would be estimating a linear model here with salary, sales. We're going to be calling this data set right here that we have, and we will be storing the results as model underscore CEO cell 2. And then we would be summarizing this. And let me run it up to here. So this is the model that we have here. So the formula is salary regressed on sales. And these are the coefficients that we have here. So this is the what we call the linear model because sales is measured in millions of dollars, but it's not logged. And then salary, the dependent variable, is measured in thousands of dollars, but it's also not logged. So these are the coefficients that we have here. So the way to interpret these coefficients here are that, for example, this coefficient here, we would interpret it that for each additional $1 million in sales, because millions of dollars is the unit for sales. So for each additional $1 million in sales, we would have as basically 0.155 thousand dollars or $155 increase in salary for the CEO. That's how we're going to interpret this coefficient. If we actually plot this using the GG plot, and we're plotting sales here versus salary, this is the graph that we're going to see. So this is how the plot of salary right here against sales looks like. And one thing that's very noticeable in the data is that we have some higher values both for sales right here. These are the higher values for sales, as well as some higher values for salary. And so what happens here is that a lot of the points are located here, but because of these extreme values, they're kind of more squished together on the plot here. And that's one of the disadvantages about using uh, the the variables in levels as opposed to logging them. Okay, so now let's um, basically look at the logs of the variables. Now we already have the logs created and included in the data set, but if we did not, this is how we create the log of a variable using the log function. So here we would be actually using log of sales. So we would be calling this variable L sales. And here we would be using log of salary, and we would be calling this variable L salary. So we're going to be using mutating, and that's going to be calculated within the CEO cell 2 data frame. So again, the pipe operator would basically put this as the first argument here, and then we would be basically assigning it back to this data frame so that we keep this logged variables. But as I said, they already exist in the data set. We already summarized them up here so that we don't have to do this again. Okay, so this is the log form. So now we can estimate the linear model. Log salary, our dependent variable, and log sales are independent variable from the same data set here. And we would be calling this model underscore CO cell 3 as the results. And now we can summarize these results and plot them. Okay, so here are these results that we have here. So these are the new coefficients that we have here. So the interpretation of these coefficients changes when we have both of the variables being logged. So here, if we see a log of an independent variable, we say for 1% increase in sales. So again, we don't say log sales, but we change the interpretation to percent. So for 1% increase in sales, we basically have a 0.25% increase in salary. So because the dependent variable is in log of sales, we also switch the interpretation to percent. So we have 0.25% increase in log of salary. So that's how we interpret the coefficient. Let's use the GG plot to summarize, to plot the data. So here we're plotting log of sales against log of salary. And let's look at this graph that we have here. So one thing to note is that, remember how we had these extreme values up here? Now we don't have them as much because that's what logging of a variable does. It kind of reduces the effect of the extreme values. And same thing here, we had some extreme values here for sales as well, but when we have log sales instead, they are a lot more evenly distributed. And this is, again, that's now the new line. And the slope of this line is, again, the interpretation of that coefficient of 0.25 that I showed you before. So again, for 1 unit increase here, we have 0.25 units increase here. Okay, so next one is the same, only that we're going to be using the linear log form. So here that's a linear, so you see there's no log for salary, and that's the log for log of sales. So that's why it's linear log, because linear is the dependent variable, but log is for the independent variable. We're going to be summarizing this model, and now we're going to be graphing this, this model as well. So here's what we have here. This is now the coefficient that we have on log of sales when salary is the dependent variable. So again, we have the linear log form. The way to interpret this coefficient is, again, if we have log of sales, we need to start with for 1 additional percent increase in sales, we would have that salary increases by 2.62 units, and salary was measured in thousands of dollars. So this 2.62 would be $2,62000. So that's how we would interpret this this coefficient. So again, for 1 additional percent increase in sales, we would have 2.62 $1,000 increase in salary. So let's look at this graph that we're plotting things. So notice that because log of sales is, the log of the sales, you see how we don't have outliers here on this x-axis. But because salary is now not logged, we still have these extreme values here as we did before. So that's how the data would look like. We log this variable here, the independent variable, but not the dependent variable, and that's how this looks like. That was basically the 3 models that we have so far. And the final case here is the log linear form. So here is when we have the dependent variable being logged, but the independent variable not being logged. And this is what we get as results. The way to interpret this coefficient here is that for each additional unit increase in sales, and sales is measured in $1 million, so for each additional $1 million in sales, we would have this coefficient times 100% increase in salary. So this coefficient times 100 would be 0.0015% increase in salary. So for each $1 million increase in sales, we have 0.0015% increase in salary. And this is the graph that we have here. So notice that now we log the salary here, but we did not log the sales. So here we still have some outliers here as well. And this is how this line looks like. So the final analysis is here to repeat the same thing with wage. So we would be reading in the data set again, wage1.csv, calling this data set now data frame wage 2, we would be selecting wage from this data set. We would be selecting wage to data frame right here. We would be selecting wage, log wage, and education, and we would see the first 10 observations. So this is how this data set looks like. Um, so this is wage in dollars, log wage, and then education in terms of number of years. So the linear form would be linear model, wage regressed on education, coming from this data frame here. We would be summarizing this model and then plotting it. And this is what we would see here. So we interpreted these coefficients before. Basically, if education increases by 1 year, we would have $0.54 increase in wage. And this is how this graph looks like here. This is the data sets. They look more aligned on a line like that because education is actually an integer. So we have 5 years of education, 6, 7, 10 years of education, and so forth. So that's why the data set looks like that. So this is how education looks plotted against wage. And again, the slope of this line here is that um, 0.54 that we found the coefficient from before. And if we are doing the log linear form, we would actually be regressing the log of wage on education. And let's summarize and plot this model. So if we have the log of wage regressed on education, this will be the coefficient on education. It would mean that for 1 additional year of education, we would have 8% increase in wages. And this is how this looks like. So notice now we have log of wage on the vertical line, not wages. And here we still education. That's why it's the log linear form. And this is how this slope looks like. So this would complete the presentation of simple regression models in R. Thanks for watching.